I said we were going to go back to a couple of the cases that I sort of glossed over in the last class. I wanted to go over several examples of flow situations where you can look at the Navier-Stokes equations and simplify some terms and just show them all to you at once without going into details. But now we'll go back to some of them and look at them in more detail. Okay? The first one that we're going to look at is the flow between parallel plates. So these situations that we're going to discuss now are situations where it is possible to simplify the Navier-Stokes equations to the point that we can actually get a full solution for velocity, pressure, everything. So we're going to consider two parallel plates which are infinite. So these are sort of idealized situations, and from the middle center line to each plate we have a distance h, and our reference frame is x, y, z, and the flow is steady, and it's flow parallel to the x-axis. So v is equal to 0 and w is equal to 0, and we only have the u component of velocity. So remember the equation of continuity. Continuity in differential form said that the divergence of velocity is equal to 0. That is equal to du dx plus dv dy plus dw dz. But v is 0 and w is 0. So for this case we have that du dx has to be equal to 0. So the flow is 2D and symmetric in the z direction. We get that u is equal to only a function of y, only a function of the coordinate vertical in my picture. So now the Navier-Stokes equations, I'm just going to flash the Navier-Stokes equations to you here. There they are. And then we're going to delete them again. But we're going to look at them so that we can we can very easily simplify some things. Okay? So u is only a function of y. So this is 0, this is 0, velocity, v is 0. So everything that has v is also 0. V is 0. W is 0. And w is 0. This is 0. All of this is 0 because w is 0. All of this is 0 because v is 0. And again, u is only a function of y, so this guy is 0, this guy is 0. V, it's steady, so this is 0, this is 0. Right? So we are only left with this term multiplied by the viscosity, and these other two equations where if we take in this case gravity in the y direction, then this is 0 and this is 0. Okay? So we're only left with, and I can write it up here maybe, the Navier-Stokes equations. I wasn't too clever with where I put this, but let me just write the first one. It's 0. 0 on the left hand side. So let me just write it in the same order I have here. So on the left I have minus dp dx plus mu second derivative of u with respect to y equal to 0. Right? That's the first equation. This guy. Yes? For the second equation, I'm just going to have minus dp dy rho g equal to 0. And the third equation is going to be minus dp dz equal to 0. Okay? But I'm going to make this disappear so I have more space now. And you saw how we did that. So let's see, minus dp dy was the other one. And we also had minus rho g equal to 0. And the third one was minus dp dz equal to 0. Here is our Navier-Stokes equation for this case. The last two equations tell me that pressure, I could integrate this. You can see that pressure is a constant with respect to z, and I can integrate with respect to y, and I'm going to have pressure equals to minus rho g y plus some sort of constant, which is a function of x. Let's call it f1 of x. Because x doesn't appear, so we don't know if there's a function of x that gets turned into 0 when we apply the partial derivative. So this is consistent with these two equations. Correct? These two equations tell me that p has to be a linear function of y multiplied by rho g, and possibly there could be a function of x there. Basically, this only tells us that pressure varies hydrostatically in the y direction. It's no news. Okay? Then sorry, yes?
I'm sorry. How did you get the integrate?
So we integrate this, and this one tells me that pressure is a constant with respect to z.
Yeah.
Then we integrate this. What do we have in this guy? We have dp dy is equal to minus rho g.
Oh, okay.
It's a linear function. I integrate that, and it gives me that. I integrate minus rho g with respect to y. It's minus rho g y plus a constant. But that constant could be a function of x because I'm taking partial, so we don't know. So we just leave it there. So remember, we're taking g vector to be equal to 0 minus g 0, right? So it goes in the minus y direction with the value g. This is our vector. Okay, so now we're going to rewrite the first equation. For the first equation, I'm going to make a little bit more space here. And u is only a function of y, so there's no need to write partials anymore. It's an ordinary differential equation where the second order derivative of u with respect to y, okay, is equal to, I'm going to move this to the other side and divide by mu, and I have 1 over mu dp dx. So I integrate once, and I get du dy is equal to 1 over mu dp dx times y. Again, it's a linear function plus a constant, c1. Yes? It's just u is only a function of y, so I don't need to use the partials. We obtained that from the continuity equation. Good. So now we integrate again. And we get u is equal to, and so this is y. The integral of y is 1/2 y squared, and so I get a 1/2 here. So 1 over 2 mu dp dx is a constant when I'm integrating with respect to y squared plus c1y plus c2. To determine Cy and C2, we need to find some boundary conditions. Our boundary conditions are that the velocity has to be equal to 0 at both walls, which is y plus and minus h. So while you think about that, I'm going to, I'd rather just manually erase some things so that we can leave that in front of us than clear the whole slide while you think about what I've just said. So to get C1 and C2, we need boundary conditions. And those boundary conditions are no slip at the walls. So U is equal to 0 at, what is it? The two locations of the walls are y equal to plus or minus h. There's no slip boundary condition, right? If we put this back into here, so for, well, we immediately can see that C2 has to be 0, no, C1 has to be 0 actually. I'm going to go straight to the answer. C1 is equal to 0, C2 is equal to, if you put either plus or minus h, to be able to get u equal to 0, you just solve for C2 and you get minus 1 over 2 mu dp dx h squared. Just putting either h or minus h in this equation. So we have C1 and C2, so we can write finally the answer for the velocity immediately, which is u equals to 1 over 2 mu dp dx y squared minus h squared. This is the result we've already discussed before, but we discussed it without proof, which is that you get a parabolic velocity profile between the two plates. There, sort of parabolic. Otherwise known as Poiseuille flow. Now, we can get a lot more stuff from this result. For example, we could get the volumetric flow rate. We can get, now we can go back and look at the pressure and so on. So let's, because this is a very standard problem, let's go that extra step. This is a very, very famous standard result that is used incredible amounts of times. Yes? This is a pressure-driven flow. So if you impose a pressure change, you will get that velocity. If the pressure difference was 0, there would be no velocity. So this is what it's telling you. The greater the pressure difference, the faster the flow is going to go. It's driven by the pressure difference. But, so the pressure difference really drives everything. You can find the volumetric flow rate is going to depend on the pressure difference between 2 points. The average velocity, if I want to calculate, is going to have this delta P up here, and this is what we're going to do next. So this is a pressure-driven flow. We're still doing Poiseuille flow, as it's called. And we have a result for the velocity, and so let's look at the volumetric flow rate. Volumetric flow rate, let's, we're going to use, we use the word Q, but I'm using a smaller case Q because it's actually per unit, since I'm looking at only the two-dimensional plane, which is my the plane of the paper where you're drawing this picture, or the plane of the screen where you're looking at this right now, per unit depth is this volumetric flow rate. So it's volumetric, but it's like a 2D result. So let me explain. This is equal to the integral between minus h on h of u dy. So you see my area is actually just a linear dy because I'm taking a unit length in the depth of the paper. Does that make sense? So it's y times, okay, so times 1 basically. And we can integrate this, minus h to h, and it's 1 over 2 mu dp dx y squared minus h squared dy. So I get q is equal to minus 2/3 h cubed mu times dp dx. Of course, the volumetric flow rate has to be positive, so you can see here that dp dx has to be less than 0, which means that the pressure decreases in the direction of flow. Like I was sort of making you imagine that the flow is sort of falling through the slope of the pressure gradient, right? If you want to sort of get a mental image of the pressure driving the flow, that's what I can think of. And dp dx is less than 0, the pressure decreases in the flow direction. Or in other words, the flow has to be from larger to smaller pressure. Does that make sense physically to all of you? So we've got the volumetric flow rate. The next thing is we're going to do what I suggested before, which we're going to look at like 2 points in the pipe, okay? So let delta P be the pressure drop between 2 points. So we know that the pressure drops in the direction of the flow. Which are separated by, the 2 points are separated by a distance L. So we're looking at, 2 points in the pipe, and this is a distance L. And there's a pressure drop of delta P from here to there. P1, P2. So delta P is P2 minus P1. Okay. So delta P over L is going to be, in this case, equivalent to our minus dp dx. If I assume that this is linear. So we write for the volumetric flow rate between these two stations is going to be equal to 2h cubed delta P divided by 3 mu L. So if I know the pressure difference between 2 points, and I could put two piezometers or something to measure the pressure between 2 points in a pipe, then I can calculate the volumetric flow rate. If the pipe flow is laminar and therefore parabolic. For that case, parabolic flow, we can calculate the flow rate from 2 pressure measurements. And the average velocity is going to be the volumetric flow rate divided by 2h. Remember, everything is in a unit depth of the paper, right? This is infinite, they're infinite plates. Oh, sorry, I was saying pipe all the time, and really these are 2 plates. There's a similar result we're going to get for pipes, but this is 2 plates. And we have Q divided by 2h, so 2h disappears here, and we have h squared delta P 3 mu L. So that's the velocity, the average velocity. And these are useful relationships for pressure drop and rate of flow or mean velocity. We can also see that the maximum velocity, which happens at the center line, U max is equal to where's the velocity? It's not in this page, but it was it's over here actually, you see? This is the velocity inside the integral over here, right? So at the center line y is 0. So U max is minus h squared over 2 mu dp dx. Remember, dp dx is negative, so that's why I have that negative sign there, the maximum velocity. And this turns out to be equal to 3/2 of the average velocity. Yeah.
On your calculation of average velocity, you said Q is volumetric flow rate?
Yes.
Well, if velocity only has one unit term and volumetric flow rate has 3 unit terms, but we only remove at the bottom the 2h1, which is still an extra unit term.
Yeah, don't be confused by this fact, because I was trying to explain that we are looking at a unit length in the direction perpendicular to, so these are the two plates, right? And I'm looking, this is 2h, the distance. I'm looking at a unit length in the direction perpendicular to the paper. So there's a 1 implied, 1 meter or whatever unit it is, implied in all of this derivation. And that, you can see that from here, where my unit area is only dy, it's dy times 1. That's the area, times 1 in whatever units you choose to use, because I'm looking at just one cross section of these infinite plates. That's why. So from there, you can see the units of Q are only have two lengths, right? 2 lengths and 1 time divided by 1 time, and so that's consistent with this. And basically, what I want to show here is that everything is known. All the details of laminar flow between two parallel plates are completely obtained from the Navier-Stokes equations. It's no mystery here. The next case that we're going to do is Couette flow, which is the one I suggested previously, where the bottom plate is fixed, the top plate is moving. You know, I wonder whether Poiseuille flow is also parabolic, but I believe I have stretched the title of Poiseuille. I believe that Poiseuille really applies only to the pipe version, where you have parabolic inside a pipe and not the parabolic between two plates. Forgive me for that. I have sort of stretched I'm not entirely sure, but I think so. I think Poiseuille, the proper title is really used for the parabolic velocity profile in a pipe, not the two plates. Forgive me for that. So the next one is Couette flow. Let's get this one started a little bit and just do a couple minutes to explain it. So now we consider two plates with one plate at the top moving with a fixed velocity u and one plate at the bottom fixed. Okay, velocity 0. And now I'm going to choose my coordinates differently because there's no symmetry here, and so I'm going to have y in this direction, x in this direction. The distance between the plates, I'm going to call it b. And I want to look at the flow between these two plates. The Navier-Stokes reduced to exactly the same expression that we had before, because again, v is equal to 0, w is equal to 0. The velocity is only in the x direction, so only u is different than 0. But using continuity, we get that the u dx is equal to 0. So u is only a function of y, the same as before. And so with those with those observations, we see that the Navier-Stokes are exactly the same as we had before. The only thing that changes really is the boundary conditions. And this shows you how important the boundary conditions can be to your solution of a partial differential equation. So boundary conditions are different. We have that the velocity has to be equal to 0 at the bottom wall, of course, because there's no slip. So velocity is equal to 0 at y equal to 0. And we have, of course, the velocity at the top has to be equal to velocity of the plate. So u is equal to, oh, this is a, let's use a capital U. Let's see if I can differentiate between the two. U is equal to a capital U at y equals to b. So now we're going to get simply, with the same equations that we had before, new values for the constants of integration. From these different boundary conditions. And they are C2 equal to 0 and C1 equal to U, the capital U, the velocity of the plate, divided by B. So the result is that lowercase u, which is a function of y, we said, is equal to capital U, the velocity of the plate. I wish I'd used a different letter, but it's too late. Times y divided by b, plus 1 over 2 mu dp dx y squared minus by. And it's normal to write this in a non-dimensional form by dividing by capital U, the velocity of the top plate, and we get U over big U is equal to y over b. So this is not non-dimensional now. Let me write this out. B squared over 2 mu capital U dp dx y over b times 1 minus y over b. So we've taken b squared out of this thing so that we would have everything in looking non-dimensional. It is non-dimensional indeed. So this term over here, this whole coefficient will determine the shape of the profile. This determines the value of this determines the shape of the velocity profile. The simplest co-ed flow is found when dp dx is equal to 0. And in this case, note that even when dp dx is equal to 0, there is a flow. Because all of this term is going to be 0, but you still have a linear relationship, basically. You get, for that case, the velocity varies linearly with y. This simplest case results in u over capital U is equal to y over b. Okay. So let me show you some, and we'll be finished for today. Let me show you some profiles, how they look depending on the parameter, this parameter here, b squared over 2 mu capital U times dp dx. These are the different options. So for the value of this, we call it capital P. This capital P is this coefficient. Capital P is this coefficient minus b squared over 2 mu u and times dp dx. And you see some interesting things there, which is for some choices of this parameter, you could have actually a backflow. So the top could be moving, this is the top plate moving with velocity capital U, and you could have a bit of a backflow here, which is interesting, a reverse flow at the bottom related to, just because of this combination of parameters. If this was equal to -3 or -2, you get that. If it's 0, you get the straight line. It's a straight velocity profile, depending on y. You see? That's Couette flow. Okay, let's finish here, and I'll see you next week. Homework due today. Don't forget.